Hi. So today let's discuss the value function approximation and a well-known method of that called stochastic gradient descent. Okay. So the reason that we need this value function approximation is that sometimes our state space or action space is too large. Okay, if it is finite, and there might be a very high demand of the memory for storing all those spaces and those values, right? And sometimes we might just directly see that some continuous space for the state and actions, right? So in those cases, then we might just instead of storing all those states and actions in those large spaces, especially they are continuous, so instead we simply use some functions to approximate the values, the v functions or the q functions, right? Instead. So, and another reason behind this approximation is that sometimes we might need to generalize the behaviors or the performances of our algorithms on some states that might be close to some state that we have seen before, but those are not showing up in the training data set or the experience, right? So those would be another reason that when we might need the generalization or the approximation for the value functions or the q functions. Okay, good. So now let's. So normally we use the notation. Okay, so this would be the value function given state S and this W with some arrow on top. That would be a vector. Okay, with some with let's say d dimensions of in this vector W, and that would be some parameter. Okay, in some function that we're gonna approximate this value be hat. Okay, and we want it to be closer to the true value of this value function, v pi f s. Okay, so this w, you could interpret this all those dimensions of w such as some parameters or coefficients in a linear regression model, or you can just interpret this w as some weight and biases in the neural networks, right? So any method that you can imagine for as long as it's just some supervised learning method, and that'll be able to approximate this value function, right? But normally we just use those methods that are able to perform well in the reinforcement learning, right? Because essentially RL problems are not exactly the same as supervised learning problem. Okay, good. So let's first have a look on the previous, the traditional ones, the algorithms that we see before. And so in the Monte Carlo, so the ground truth or the target that we're gonna approximate to be this GT, right? And in the TD0, so that'll be the immediate reward of RT plus 1 and times the gamma times the v hat and taking st plus 1 and wt as a vector. Okay, in the dynamic programming, that would be the expectation over the policy pi and of the immediate reward rt plus 1 and the discount future reward gamma times v hat. Okay, so the measure that we normally use for the for measuring how well is this approximation, right? If that is closer to whether it is closer to the ground truth or to the target that we're gonna approximate, or it's still far away from that. Okay, so normally we can use the mean squared error called MSE as mentioned here, or sometimes we can use the square root of that MSE. Okay, it's called RMSE. Okay, so either could work here. And we often refer to those errors as the loss, right? And so in MSE, we have the summation over all the states, and here we have a mu of s, so that'd be just some distribution over s to indicate the importance of different states. So that is not very important, at least in this part. But so the important part will be this square of this distance. Okay. So this distance measures the difference between the target v pi and the one that we have for now. That would be the v hat. Okay. That we're gonna use to approximate this v pi. So let's now go into this stochastic gradient descent method. That would be a very famous and well-known method for the value function or for any function approximation, right? So essentially, stochastic gradient descent, or SGD, it is working by adjusting the weight vector, so that would be the W, right? After each example or each observation or each tuple, right, by a small amount in the direction that would most reduce the error on the example or on this observation. Okay, so and here it's saying that it can update or adjust the weight vector in the direction, okay, and which direction that we can reduce the error mostly, or we can most reduce the error with this observation. Okay, so let's see how it is working. Okay, so mathematically, so we define, so this is just some updating rule that we define, right? So we define this WT plus 1 for the next time step to be using the WT. So here I put this in the highlight blue color. So WT minus a half of alpha times the gradient of this square distance. Okay, so the reason that we have half, that'll be very simple. That's simply because that we are gonna take the gradient of or taking the partial derivative of some square function, and we just use this half to cancel that, right? And another very important part for this blue highlight part for this minus side. So what we wondered that why we're having the minus instead of a plus, right? So that we have a plus here but not a minus, right? So that'll be a key question to this approach. Okay, and we will explain this very shortly. Okay, so after we take the gradient of this square distance, then we'll cancel that with the half. Okay, so this alpha will be just some positive coefficient or positive parameter for us to control the learning rate. Okay, that would be the step size. And after taking the first step of the derivative, that would be this part, right? Canceling the square and the half. And by the chain rule, it's very important to have the other part, okay, by the chain rule. That would be, we still need to take the gradient of this v hat because we have a WT here instead of this function, right? So we're gonna take that with respect to this WT, right? So here in the target, we're gonna assume that this will be just some fixed number, right? So here in this target, we're not having any gradient to take furthermore, right? So the place that we're gonna take another gradient or to take another multidimensional partial derivative, that would be the second part, right? So we must have this part here. Okay, good. So what is a gradient? So that would be just a column vector. We have a transpose here, the column vector of all those dimensions. We have d dimensions of those partial derivatives. Okay, for any function f. So this f will be simply so it can be this for the first step and it can be this for the second step here, right? So those gradients. So that would be this function taking the partial derivatives of this function with respect to all the w's. Okay, so here we have two subscripts, and the first one would be the time step t. This is just for t, and we have all those d dimensions. Okay. All right, so here we have some notes that alpha is the step size parameter, and which is positive, and this would be just the convector of the derivatives. Okay, and that's called gradient. Good. So next comes to the key question, right? So we just ask why this is true, that we have this SGD to adjust the W in the correct direction that would most reduce the error, right? So and we mentioned that the answer comes from this minus sign here, right? Okay, so why is that? Let's have a further look. Okay, so for example, let's suppose, okay, so now we're gonna to simply let this this function, this v hat, to be the f that we're going to refer to. Okay, so let's say that this, if the partial derivative of v hat, for example, with respect to wt1, we just omit t, so with respect to w1, let's say if that is a positive partial derivative, okay, so it means that if we increase w1, then v hat has to increase. And if this ground truth or this target is greater than the approximation we had, if those are true, okay, and then we can see from this expression, okay, so what will happen is that now we have this to be positive, right? So alpha is a positive, and then we have this to be positive. We said that this is bigger than the other one, right? And then WT will plus a positive thing, so this will make WP plus 1 bigger, and that'll be bigger just in first dimension because we're just talking about the first dimension, right? So this whole equation is multi-dimensional. Okay, we're just talking about the first dimension here, W1 dimension. So this will make this WT plus 1 bigger in the first dimension. Okay, and further, again, by the assumption that we have, let's say if this is increasing in W1, this V hat is increasing in W1, okay, and then this V hat is increasing, right? Because we said that here W1, this is increasing, right? So by this, if we increase in W1, then V hat is increasing. So we have V hat increasing, right? Then V hat now, because it is increasing in a very small step, right? So we must know that now V hat, it becomes closer to the true value. Okay, so this distance becomes smaller, and that successively adjusts this weight so that this weight makes those distance smaller. Okay, good, very good. So now let's go to another example, and suppose if, let's for example in the second dimension here, okay, let's suppose in the second dimension then this is decreasing in W. Okay, so V hat is decreasing in W2. And again, we assume that this ground truth or this target is a bigger one. It's bigger than the V hat. Of course, you can suppose in the other way around, but that won't change the result. Okay, this is just for example. And if this is bigger than the V hat, then what we have is that, okay, so now we're gonna erase this, right? So this has to be negative for now because it's decreasing in this. So this is still positive, alpha is positive, then this is negative, and so here WT is gonna minus something, right? Or it's gonna plus some negative thing. So this will make WT plus 1 in this case smaller, right? But that'll be just smaller in the second W2 dimension. Okay, so by this, so when we're decreasing this, so we know that this has a negative derivative, so that V hat, it has to increase again, right? So in this case, we said that this is still smaller than this V pi, so after we increase V hat, then this is also closer, becoming closer to V pi of ST. Okay, so now we successfully verify all the possible cases. Of course, we can verify the other way around, right? But that won't change the results. And then we see that under all cases, then this stochastic gradient descent by giving this negative sign, this is very important, as long as we have this negative sign here, so that it could update this weight W to the correct direction that can help us to reduce the error or the loss on this correct direction after the observation. Okay, good. So that'll be the SGD. And now in the last, let's see some examples for the previous algorithms that we see earlier, and let's see how do we update those gradients, right? Using those gradients to update the weights. So for example, in the Monte Carlo, we're gonna just update the W by having this alpha times the GT minus the V hat of ST and W, and then multiplied by the gradient here. Okay, that's very, very important. So this GT, that would be the target, right? The actual reward after each episode ends. Then this V hat, that would be something that we're gonna approximate for this GT. Okay, and then in the TD0, so that we have this immediate reward, and what else we have is this. So this whole thing, that would be the target, and this will be the V hat that we have, right? So this will be the TD0, and of course, don't remember this gradient again. Okay, and in Q-learning, or maybe just in DQN, so, and we just use this notation from the paper of the DQN, and we keep this in the same notation as they did. So this would be the gradient of this loss, L, and this data would be just the W that we have, okay, which is denoting this parameter for the neural networks. So that would be the expectation over the state, action, and next state, and then this would be the target, right? So that we have, which is the immediate reward plus the sum of discounted future reward, gamma multiplied by the. So that would be very important to notice that we have a maximization over by choosing some A prime for the next state S prime. So this would be a so-called off-policy learning, right? So you can refer to the previous videos. So in contrast to the on-policy learning, so now we're gonna, by choosing some epsilon greedy policy A prime, simply for the next state S prime, okay. So here we're gonna change this action immediately, right? Just at this time step for the S prime, where we are not following the previous policy, right? So this value is computed from the previous old policy, right? So from old policy. And here in the target, we do not follow the old policy. We're gonna immediately change that, and we're gonna use this some epsilon greedy strategy or this policy, right, for us to just explore or just not explore, right? So this is just still using the greedy policy that we're gonna to try to maximize the Q, right, by choosing some A prime, okay, under the S prime. So something important to notice is that no matter we're having the target or the Q that derived from the old policy, we can always compare those two things, right? The reason is that it's just the target decomposes this Q into two parts, right? The first part is this R, and the second part would be the sum of discounted future rewards, right? By taking some greedy policy A prime. So it's just, the difference would be just this, right? So, but after we sum those together, this becomes the Q, right? That is essentially that would be just the Q when we are facing the current state and action, right? So that would be exactly essentially equivalent to the thing that we're going to talk about on this after using this old policy that we have, right? So here what I means that this in the target part here, we're just decomposing this into the immediate reward and all the future sum of future discounted rewards, right? But from the old policy, the one that we're going to approximate for this Q function, that'll be just the everything that we have, right? So that would be the whole queue that we have here, okay? So that we can compare across those two different representations, but they are talking about the same thing, right? So that we can just compute the loss from those two things, okay? And of course we have this gradient, and don't forget about that, okay? All right, so then you can refer to more details of DQN that we have discussed earlier in the other episodes, okay? All right, so today we discussed the value function approximation, and we understand that why do we need those approximations, and the very important method called stochastic gradient descent for us to implement those approximations in different algorithms, right? So and we see that we have also provided some examples to verify all different situations that we see in SGD method, and in each cases then we can very successfully verify that this SGD it works, and it helps us to update or adjust the W weights in the correct direction that most reduce the error or the loss, which is the distance between the approximation and the ground truth, which is called target in RL problems. Okay, so that'll be everything for today.